Welcome back to Historical Geology. I'm going to continue on with Chapter 16 on the Paleogene and Eogene of North America. And now we're going to move on to the Circum-Pacific Orogenic Belt, which really, to most of us, we know it as a ring of fire, which are the volcanoes and earthquake activity that occurs around the Pacific Ocean basin. First, looking at the Japan part of this. One interesting thing about Japan has a back arc basin. And what that means is that there's a mid-oceanic ridge, a spreading center behind the arc, and that's in the Sea of Japan. And Japan was probably attached to Asia during the Mesozoic, and then in the Cretaceous time, it was separated probably by something called trench rollback. So looking at this picture here, as subduction of the Pacific plate occurs in the Japan trench, what happens, this steep subduction starts rolling back toward the west here, and it's going to pull the arc along with it, separating it away from mainland China in this case here, developing this back arc basin. Now the lithosphere on the landward side of the island arc is stretched and thin, and that becomes this spreading center, the Sea of Japan. So that's one interesting thing about Japan, but we know Japan is very active. It has these big stratovolcanoes like Mount Fuji, and it is an ocean-to-ocean convergent boundary now, and it is an island arc, The other place that are also island arcs is going to be the Aleutian Islands. Besides looking at the Aleutian, we'll look at some of the Eastern Pacific. So when I say Eastern Pacific, I'm talking about the Western United States and the Western South America. And so we'll look at the Cascade Range, the Andes Mountains, and then how the East Pacific Rise, the mid-oceanic ridge, made contact with the trench during the Oligocene epoch. We'll talk about how that formed the San Andreas Fault. And then we'll talk about what happened to the Farallon Plate and the current plates that represent the Farallon Plate, the Cocos and Juan de Fuca plates, and how all this developed here. First, let's look at the Aleutian Islands here. So the Aleutian Islands, again, are an ocean-to-ocean convergent margin where we have an island arc, so it's Japan type. And so you can see here are the Aleutian Islands. So there's about 80 volcanoes. Most of them are active. And here we're seeing the Pacific plate subduct into the Aleutian Trench, and then there's an ocean basin behind it, ocean to ocean. And this is a 2017 eruption of the Bogoslav volcano, which sent ash about 30,000 feet, and airplanes had to cancel their flights over the Arctic here because of all that ash. But they're really spectacular volcanoes. In fact, they're always steaming with fumarolic vents here. So these are actually gases coming out of these volcanoes right here. Now, looking at the North American Cordillera. So remember, Cordillera refers to all the mountain ranges in the western United States, all the way from Alaska up here, the Brooks Range, all the way down into Central America here and Mexico. Now let's look at this Cordilleran igneous activity. The first range we'll look at is a Cascade Range, and it really stretches from northern California, which includes Lassen Peak and Shasta, and it goes all the way to British Columbia, where there's a Mount Garibaldi there, Cascade volcano. And this volcanism goes back to about maybe 30 million years, which is into the Oligocene epoch. And in California, Lassen Peak last erupted between 1914 and really 1921 was the last small eruption, but the big eruption was May of 1915 when there were some large eruptions. And then also St. Helens, we know, had the very large eruption in 1980, but also there's been other eruptions in 2004, and there's been some other activity in the last 10 years as well. So looking at these Cascade volcanoes, so this is actually Lassen Peak, which is really a large lava dome. In fact, Lassen Peak first started erupting about 27,000 years ago. And again, the last eruptions were in 1915 to 1921. So again, very active lava dome. And then as we go farther north, these are some spectacular Cascade volcanoes here. This is Mount Hood, and there's Mount Rainier in the background. But you can see there are all these snow-capped stratovolcanoes, very picturesque, subduction zone volcanoes, stratovolcanoes. So what's happened is we're subducting the Juan de Fuca plate in the Cascade Trench, and we're developing all these Cascade volcanoes, which really stretch from Lassen Peak up here to went to British Columbia, which includes Mount Garibaldi. Going farther south into the Andes, so the Andes are very similar to the Cascades in that we have an ocean to continent convergent margin, but in this case we're subducting the Nazca Plate under South America. And then we're seeing the Andes volcanic mountains or the volcanic arc, and there's and a baffle. The magma chambers are forming down at depth here. The history of the South American origin or the Andes Mountains really starts off when Pangaea begins to rift, and really by Cretaceous time the South Atlantic begins to really separate or form, and Pangaea rifting, where South America starts moving westward and starts to override that Nazca Plate, and you develop that convergent margin. So we started off in the Triassic with a passive margin here, but then as Pangaea broke up, we developed an active margin, and we started forming these high Andes Mountains and Dientite magmatic arc. Now, looking at other Cordilleran igneous activity, we want to talk about the Columbia River Plateau. And this area is considered a flood basalt province. This Columbia River Plateau is underlain by more than 200,000 square kilometers of Miocene basalt. And the volume is estimated to be 170,000 cubic kilometers of lava. And they're probably due to some mantle plume. And so again, we're looking at this Columbia River Plateau region, which extends really into the Modoc Plateau of Northern California, into Idaho, part of the Snake River Plain, although there's some other type of activity going on here in terms of rhyolites and andesites, because the Columbia River is mostly basalts. And there are over 300 separate lava flows, and they average about 580 cubic kilometers each, so pretty extensive. And again, erupting between 17.5 to 6 million years ago, but most of the eruptions between 16 and 15 million years ago. The Columbia River basalts, CRB, they really are called large igneous provinces, LIPs, or continental flood basalts, because one thing we know about basalt, it's very fluid, has low viscosity, so when these lavas erupt, they spread out and cover large regions, and they essentially flatten out the topography. So that's why they're sometimes called plateau basalts, because they make a flat surface from the fluid basalts. We also find them in oceanic plateaus. We can find them in continental settings. You can see that for the Columbia River basalt, it's about 170,000 cubic kilometers. We talked about the Keweenawan province that formed in the Precambrian, the Continental Rift, and that's about 400,000 cubic kilometers. And then we mentioned the Deccan traps, which may have caused the extinction of the dinosaurs. We sort of read a little bit about that. And that was about 8.6 million cubic kilometers, so it's a huge eruption. Remember, the Deccan traps are in India. The Parana flood basalts, that separates Africa and South America. So during the Cretaceous, when we started seeing rifting of Gondwana in that part of the world, we talked about the Siberian traps, and those are the ones that occurred at the Permian Triassic mass extinction event there. And look at that, 3 to 5 million cubic kilometers of flood basalt. So certainly these have an effect on the atmosphere. And then we mentioned that they could be due to flood basalt provinces. And so here we have a mantle plume. Remember, the mantle plume travels a stationary path through the mantle, and the tectonic plates move over that plume, right? And so here we're developing some magma chambers, and we're making these flood basalt provinces. Very fluid, and they kind of spread out here. When we look at the Snake River Plain, it's mostly in Idaho. It's a depression, and it's filled with Miocene and younger rhyolite, volcanic ash, and basalt. So some of the basalt is related to the Columbia River basalts. So you can see some of those basalt lavas here. There's also something else going on here. There are these caldera complexes. And so you can see, if we look at the ages, we're looking at 16 million years here, 15 million years, 14 million years, 12, 10, 8, 9, 6, 2, 600,000 years. So there's a trend where they're older in the west and younger over here as you get towards Yellowstone. In fact, this represents Yellowstone right here. And so what's been happening here is, remember, the whole North American continent is moving away from the mid-Atlantic ridge. Pangaea is rifted, and North America is moving over that hotspot. Remember, the hotspot is stationary. It's not moving. What's moving is the continent over the hotspot. So over time, as I move this continent to the left here, these flood basalts are going to be off over here to the left. Now we'll develop a new series of flood basalts. So one way to look at it here, we see these eruptions going older in the west, younger as you get over here to Yellowstone. And we see that North America, because this mantle plume is stationary, North America has moved over this hotspot. So in other words, 12 million years ago, this portion of southern Idaho was here at the hotspot, and it's moved this distance in the last 12 million years. In fact, I have you watch a little video, a PBS Eons video on the eruption of this caldera complex when it was here at the hotspot and how it affected Miocene animals that lived in this region of North America at Ash Falls, Nebraska fossil site. So again, this Yellowstone Plateau are primarily Pliocene and Pleistocene volcanism, and there's lots of hydrothermal activity. You've probably heard of Old Faithful and the geysers, right? So that's one of the features that occurs there. There's lots of hot springs. When we look at how often Yellowstone erupts, we see that there were 3 extremely large explosive eruptions, and these are caldera type eruptions where you're erupting 600,000 cubic miles or more. In fact, they're called supervolcanoes. So we see that there were 3 extremely large explosions between 2.1 million years ago and 640,000 years ago, and that last big eruption was 640,000 years ago. Looking at those eruptions, the recurrence interval seems to be anywhere between 600,000 and 800,000 years, right? So remember, Ka stands for thousands of years, Ma millions of years ago. And remember, the most recent eruption occurred about 70,000 years ago, but that was a small rhyolite lava flow. So these caldera eruptions are really a catastrophic collapse of the volcanic system into its own magma chamber. And that's the key then, is that the magma chamber gets so close to the surface, usually around 3 kilometers or less than 5 kilometers, where the volcano is now sitting on this weak magma, and it becomes gravitationally unstable. And it begins to collapse down into its own magma chamber. And as that collapse occurs, it's going to force all that magma out, mostly in terms of pyroclastic ash. And it's almost like a piston in an engine that goes down, forcing all that ash through these ring fractures. And we end up getting a circular depression. Sometimes it's filled with lakes. In fact, this is the model for Crater Lake, Oregon, which is really a caldera type eruption. But again, emitting huge amounts of volcanic material. So looking at those 3 eruptions that occurred during the Pliocene and Pleistocene here at Yellowstone, it shows some of the extent of the volcanic ash. And so just compare, this is the extent of the volcanic ash of Mount St. Helens 1980. And you can see how huge these eruptions were the Lava Creek, Huckleberry Ridge, and the Mesa Falls ash beds. And so if we look at the ages, so the most recent one, 640,000 years ago, was 240 cubic miles. So that would be this Huckleberry Ridge ash bed. And you can see the Lava Creek ash bed was about twice as big, a little bit more than twice as big, and that's the one that occurred 2.1 million years ago. And then just comparison, Mount St. Helens was maybe a quarter of a cubic mile. Krakatoa, a huge eruption in 1883, was 4.3 cubic miles. Mount Mazama, which is the one that formed Crater Lake, Oregon, was about 18 cubic miles. And so Mount Mazama, well, you can't see it here, but that's up here in southern Oregon, which is Crater Lake, Oregon. So in other words, the volcano that used to be at Crater Lake, Oregon was called Mount Mazama. At least that's what geologists have named it. So these caldera eruptions are just huge catastrophic events.